Okay, so for the second talk of our session, we have Hemant Gouni, who is from CMU, who's going to be talking about some dependency tracking using substructural logic. And I want to say that this is also one of the distinguished papers of POPL'.
All right, let's talk about substructural dependency tracking. First, okay, so what is dependency tracking? Basically, if I'm holding a computation in my hand, I want to know how its outputs are affected by its inputs. And this is super useful in a domain like security, where if my computation is processing, say, passwords or cryptographic secrets, I want to make sure that it's not leaking information about those to, say, the internet. But the sorts of data provenance and separation properties that emerge out of dependency tracking are also super useful for things like, say, concurrent and distributed systems, and program slicing, and build systems, and reactive programming, and so much more. But in all these cases, there's certain extra questions that sometimes arise that lie just beyond the reach of standard dependency tracking techniques. Things like, how often do I depend on this piece of data? And if I am said to depend on this piece of data, is that dependency guaranteed? And finally, in what order am I inducing these dependencies? And our work is an attempt to answer all these questions in a unifying and satisfying way. And so, understanding all this dependency tracking stuff is really why we're doing this work, but I think it's a lot easier to understand how we did this work, starting from the substructural part of the title. So let's do that. And in particular, the place I want to start is affine types in Rust. So if I'm in Rust, and I've got this capital S string bound to this variable x, and I pass x to func1, and then I pass x again to func2, Rust will give me a type error. Rust will say, well, you already consumed x once when you moved it into func1. You can't consume it again when you want to call it on func2. And this is because data in Rust is ephemeral. You can only use it a single time. And it's exactly this idea of ephemerality, or change over time, in this case, variables being deleted, that leads to resource reasoning. And we can generalize from this picture of singly bounded consumption to finitely bounded consumption using something called bounded affine types. And a simple syntax for this might look something like this, where if I have I have this function f whose signature goes from nat with 3 fuel emojis annotated to a nat. And the semantics of the fuel emoji is that each one indicates one allowed usage of the variable, or of the input variable. So I'm allowed to use x twice or thrice, but I'm not allowed to use x 4 times, because by the time I get to the 4th usage, the type checker says, okay, you've run out of fuel for x, so you can't use it anymore. So no dice. And the thing to observe here is that the number of fuel emojis on the input dictates the structure of the body of f. And so to get from this picture to ours, all you need to do is sort of flip the picture around a bit. So instead of using restrictions on the input to create resources, you want to use restrictions on the output to create resources. And that might look something like this, where I have this function g that goes from a coin nat to 3 coin nat. And the meaning of the coin nat on the input is that whenever you use the input x, it induces a single coin worth of resources. And the meaning of the coins on the output is that any valid body of G can't use more than 3 coins worth of resources. But I've actually lied to you slightly here, because when you move from the input picture to the output picture, what you start caring about is not usage of variables, as in the input case, but the running of computations. And this is a really, really important and deep theoretical choice that is actually forced and not a design choice at all. And so the way to begin to understand this is, okay, you can think of the coin nat type as a thunk, or a suspended computation. And you can think of all these exclamation mark operators as forcing the thunk, or running the contained computation. So what matters for inducing a coin is not mentioning the variable x, but running the computation it contains. In particular, something you can do that's totally valid is binding y to the result of running x, inducing a single coin, and then using y any number of times you like, because y is just a type nat and doesn't induce any coins. It's just a value. And so to understand why we're focusing on this running of computations versus mentioning of variables, which might seem like kind of an arbitrary design choice, you might think of the semantics of the fuel emoji as being consumed by the body of f, whereas the semantics of the coin emoji is to get produced by the body of g. And so this idea of consumption versus production sort of really nicely characterizes co-effects versus effects, where co-effects are all about consuming variables by using them, and effects are all about producing things by virtue of running computations. And there's a stronger proof theoretic justification for this in our paper if you're not satisfied with this explanation, but for now I want to move on to some examples. So the first example will return us to dependency tracking land, and in particular we want to track very coarsely, not as powerfully as the last talk, but very coarsely some measure of the amount of information regarding some password that we depend on. So this password checker module is going to export some affine resource lock, where affine just means the quantity matters. And it's going to export this method check that takes a password as a string and returns me a Boolean that says whether I got the password attempt right or wrong. That's also annotated with this lock. And so when we go to use check, if we use it just once, we induce a single lock in the type. If we use it twice, we induce 2 locks in the type. And if we use it twice but only annotate 1 lock in the type, then we get a type error because the type checker knows, well, you've produced at least 2 locks worth of information about the password, so this is no good. So like go away and do something else. So you can't do that. But interestingly, something you can do is in the first line here, you can choose to annotate the type with 2 locks instead of just 1 lock. And the reason for this is due to a principle called strictness, which specifically says, or rather lack of strictness, which specifically says, given a dependency or given a dependency set or a resource context rather, you can tack on another resource onto it, here a diamond, basically for free without doing anything. And so you might wonder what reasoning abilities we get out of removing this ability to give ourselves more resources for free. And it turns out it lets you reason about authorization in a nice way. So this authorize module starts by declaring this strict resource diamond. And it also declares this method authenticate, which takes in, again, a password attempt as a string and returns me, if I get the password wrong, it gives me a unit with nothing on it. And if I get the password right, it gives me a unit with a diamond on it. So the idea of this authorize module is that the only way for me to get a hold of a diamond is to witness a successful authorization. That's the only way for me to do it, because again, I cannot give myself a diamond for free, and there's no other way to get a diamond except by calling authorize. And so if you have some sensitive computation that you want to guard in your program behind authorization, all you have to do is mention a diamond in one of its arguments, and then anything that hasn't witnessed a successful authorization and therefore doesn't have a hold of one of these diamond tokens to give to it cannot call that computation. So just to flesh out the example a bit here, you can call authenticate with the password attempt string, and if you get the left injection, then you got the password wrong, and you got to maybe run some cleanup logic or error handling or something else. But if you got the password right, then that's the exciting case, and you have this token that's a unit with a diamond on it. And to call the secured function, you can pass it an integer with the diamond from the token stapled onto it, and then pass that whole package into the secured function, which will type check because it witnesses your successful authorization, and that's very good. And our final example is going to be protocols or seccomp. So I'll go through this slowly. And so there's this pattern in a lot of really high security or sensitive software like web browsers or web servers where they start out needing a lot of permissions because they say need to create lots of temporary files or spin up network sockets or take locks on a bunch of resources and so on and so forth. But once they've reached their running state, they really don't need all those permissions anymore. And so what, like, say, Chromium does is it tells the operating system, OK, from this point forward, I'm not going to need most of my permissions anymore. And so I'm only going to use some little carved out piece of your API surface that's like safe for me to use. And if I violate this contract with you, kill me, like terminate my process immediately because I've been compromised. And so we can encode this really widespread pattern, as it turns out, in a lot of secure software in our system by working with what are called immobile resources. So we declare these 2 immobile resources drop and high, and what an immobile resource is when you mention it in a resource context, all it means is roughly it can't move around. There's a slight extra technicality here that I'm not mentioning that you can look to the paper for full details on, but just continuing, we go on to declare a structural resource low, which just means it's not restricted at all. So low is just, it can appear anywhere, it can be weakened, or it can be added into your resource context for free. There's no restrictions on it. And then we declare these 3 operations, drop, high, and low, that each induce one of these resources. And so a valid pattern of usage is to run the high operation, and then run the low operation, and then drop privileges, and then do a low operation. That's totally fine according to this protocol. And another valid pattern of usage is to never call drop at all. So you can do low, high, and that's totally OK, because you just never call drop. But what's not OK is for you to do a high operation, and then drop privileges, and then a low operation, and then do another high operation right at the very end. Because now you've dropped privileges, which means you've got this contract with the operating system, and then you're still trying to do a high operation after it, which is no good, right? So that's a type error, and the program rejects it, and the type checker rejects it because it mismatches the declared protocol in the type. And so the thing to take away from all these examples is that the production perspective characterizes naturally a very different range of resources than the consumption one. And so like with this quantity-sensitive leakage example, it's very natural to think of a computational process as like producing or generating some information that you then need to keep track of and control in like a quantity-sensitive way, rather than thinking about it as some sort of matter of subsumption, I think. And especially with capabilities, like the structure of a capability is that it's a token produced by some authorization or validation computation that you can then present to other things that need authorization or validation, and not, it's sort of confusing to think about how you'd model it as a matter of consumption. And the picture is slightly less clear for the seccomp example, because of course you could encode that using some sort of like object-oriented linear type state, right? That's a very classic maybe use case of it. But it's interesting to think about the ergonomics of like passing around the entire operating system kernel as like a type state object, and trying to work with the protocol that way, versus just selecting out the operations you're interested in and sort of declaring an ad hoc protocol on some ambient operations that you want to control right at that local context, as we did. So there's a sort of an argument for the production perspective there as well. And there's more examples in the paper. And it turns out we get a 3-for-1 deal on capability, quantity, and protocol safety. And to explain how we do that, I have to pull back the curtains a bit and explain. So when I showed you this thing about, when you have a resource context in your hand, you can tack on, say, a diamond onto it for free. I was really applying this principle called weakening from substructural logics. So we were weakening a diamond into our resource contexts. And when we removed that ability, we were removing weakening from this diamond resource. But really what was going on under the hood is that there's this subsumption relation defined on resource context that lets you go from a resource context without a diamond to a resource context with a diamond. And when we made diamond strict, we made it so that that case of the subsumption relation was dropped away from diamond and could no longer be used to obtain a diamond for free. So diamond was a strict resource. And likewise for contraction, when we made locks sensitive to quantity, we removed this rule of contraction that says, you can collapse 2 locks into a single lock. And so we made lock into an affine resource. So we removed that case of subsumption again. And the situation is very similar for exchange. Like when we removed this sort of pseudo commutativity property of high and drop, we again removed the case of subsumption that lets you commute these resources. And then we ended up with immobile resources high and drop because we removed that case of subsumption. And so you can mix and match all these modes according to this mode lattice in our system, and actually this is only part of the mode lattice. But really the takeaway here is there's this subsumption relation on resource contexts that fully sort of captures the substructural properties of our system and everything we're interested in that respect. And with that subsumption relation in our back pocket, we can state soundness now. So you can read this as, if we've got a well-typed resource, or sorry, if we've got a well-typed program under some resources A1, A2, and forcing that program evaluates it down to a value, and produces some resources B1, B2, then the resources B1, B2 that were dynamically produced are substructurally compatible with the resources statically specified in the type of the program. And to see why this is so powerful and significant, I think it's really easiest to apply it to each of our safety properties. So Linden in 1976 defined a capability as a token used as an identifier for an object such that possession of the token confers access rights for the object. Okay, so really you can think of the core safety property of capabilities as this idea of unforgeability, because you need to not be able to obtain a capability or this kind of token in a dishonest way. And just as an aside, he interestingly continues to describe the sort of resource semantics of a capability, because he explicitly says it's actually okay for you to reproduce capabilities. So he's kind of saying here that contraction is okay for capabilities because the quantity doesn't matter, which is interesting. So even back in 1976, they were thinking about capabilities secretly as resources. Okay, but that aside, we can think of the soundness of the capability safety theorem as, if I have a well-typed program whose resource context contains a diamond, and that diamond is strict, then that program gets pushed down to a value, and when it does so, it produces some resources that themselves contain a diamond. So what this is saying is that when I have a strict resource statically specified in my program's type, its computation really honestly has to witness it. It really has to run a computation that honestly gives it that capability. And so the sketch of the proof for this goes something like, by soundness, we know that the dynamically produced resource context is substructurally compatible with the statically specified resource context. And by strictness, we know that we can never get from a resource context that does not include a diamond to a resource context that does include a diamond. So if you combine these two, you see that if the B1, B2 resource context on the left inequality did not already contain a diamond, there's no way we could conclude this equality because we have no other way of obtaining a diamond besides already having one on the left. Okay, and quantity safety proceeds like super similarly. So if we have a well-typed program with some resources A1 and A2, where that resource context contains n locks, and lock is affine, that program gets pushed down to a value and dynamically produces some resources B1 and B2 containing k locks where k is upper bounded by n. And the proof sketch for this goes really similarly to the last case. Again, by soundness, you have that the dynamically produced resource context is substructurally compatible with the statically specified resource context. And by affinity, you have that two locks on the left side of this inequality cannot be collapsed into a single lock on the right side of the inequality. So if you think about what would happen if the B1, B2 resource context had more locks in it than the A1, A2 resource context, it would be totally impossible to conclude this substructural compatibility that's required by soundness. So you know that the number of locks in the A1, A2 context must be an upper bound of the number of locks in the B1, B2 context. And of course, if you switch to if you drop strictness and go to the linear case, then this bound becomes exact. So k has to equal n because once you add strictness, you know that not only are you upper bounded as far as the number of locks you can produce dynamically, but for every single lock that appears in the A1, A2 resource context, you really honestly have to produce it in the B1, B2 resource context because you can't obtain any more by weakening. You cannot use weakening to resolve the inequality between k and n, so k has to be exactly equal to n. And protocol safety, well, there's a lot of different facets to this, so I'll state like a fragment of it. Basically, if you have a well-typed program with some ordered resources A1, A2, ordered meaning they lack all structural rules, all bets are off, they're not doing anything interesting. And you push that program down to a value, then it produces some dynamic resources, namely some dynamic resources where A1 must appear before A2 in the resource context, so it's a relative ordering. And one satisfying resource context for this on the dynamic side is one where just A1 and A2 in the most boring way appear right at the front of the resource context. So you have A1, A2, and then B3, where B3 is some dynamic resource. And the proof sketch for this is totally analogous from soundness, weakening, contraction, exchange, just as in the previous two cases. Okay, so there's a lot more in the paper. There's, curiously, 2 more structural rules I haven't mentioned here, which is interesting because most people think there's only 3. It turns out that you can think of the entire language I've presented to you as a constructive Kripke semantics for substructural logics, reified into a programming language by analyzing its computational properties. There's a really interesting connection between the quantification connectives in our core calculus and in our language that I haven't presented here, and this idea of shifting in linear, nonlinear, and adjoint logic. And we had to deploy this very cool new proof technique for capturing logical relations for open-ended effects because of all the quantification flying around in our language. So do check that out. And there's, of course, many more examples in the paper. But really the takeaway is that the effectful view on substructurality shown here like unifies a totally new set of tools, or sorry, an old set of tools, but a really useful set of tools newly under this umbrella where previously they were not thought to be connected at all. So that's it.
Okay, we have some time for questions.
Hey, thanks very much. This is really beautiful work. I noticed that all of your soundness theorems had a clause that said, if it's well typed, then it does produce a value and these resources.
Yeah.
So can you handle non-termination at all?
The logical relation as stated is only for terminating programs. I have worked through a step index relation on my end that I'll put out later, maybe in another paper. There's no issue with non-termination, but besides you have to talk about safety up to some idea of non-termination, right? But that's a standard thing. Yeah.
Thanks very much.
Yeah.
Yeah, thank you for the talk. You mentioned early on that your capabilities are directly tied to computations. which makes sense. But then it looks like the language that you're presenting is lazy, and normally the approach for strict languages is to put capabilities on arrow types, which are, of course, the only value that can sort of encode computation. So is there a fundamental reason why you can't do this, or is it just a different approach?
Yeah, so you can think of the resource type. Maybe it's easier for me to have a thing to gesture at here. Oh. So you can think of these resource types. Well, this is fine. You can think of these resource types as a suspension type in the sense of maybe call by push value or something. So this is like in like a polarized sense, this is like U of F, or in like a non-polarized sense, this is like a strong monad. So basically, we just have a custom little type connective that does the suspension for us, rather than sort of overloading the function connective, which most people use as a suspension connective with extra information. So we just like punted that off into another type.
Okay, but it's not like you don't think that it's more expressive. It's just a different expression.
No, it's just a different. Yeah.
Yeah. Okay, thank you.
One more question?
I'm really happy you mentioned adjoint logic, and I wanted to know if you can, like, if you don't mind giving like a little. Oh, okay. I thought the microphone was speaking to me. If you could give like a little taste of like how the adjoint logic formulation might like make things a little differently. Like, do things get more expressive or more complicated?
Yeah. So the really interesting thing about this is actually, as of yesterday, there's an adjoint logic formulation of this that my advisor works on with a different student, and so they proved that it's like formulated as this like sequence calculus sort of thing, and they proved that the type system they have there is decidable, and the way this work and that work interacts are such that you can carry over the decidability proof like totally mechanically to our system. So like indeed everything I've shown you here is decidable. You can kind of think of a lot of this as like a Kripke interpretation of a lot of adjoint logic in a certain sense that I have yet to make like super fully formal. But yeah, it's really interesting follow-on work, and I'd be interested to talk to you about it in more detail. Yeah.
Okay, sounds good.
Last question here.
Thank you for the great talk. I think at some point you showed the cuboid and you called it, or a cube, and you called it a mode lattice. And I was wondering if this was an intentional choice of words. Maybe I'm missing something and it's obvious, but is this connected to model type systems or sort of model logic?
Yeah, it's super connected to modal type systems. It's not an accident that I said that.
Could you elaborate on like the connection?
Yeah, we can take this offline, but the one sentence summary is you can think of this as basically some kind of adjoint logic, which itself is a modal logic, or like a semantics for an adjoint logic.
Cool, thanks.
Okay, let's thank him again.